is going to be organized in a table like this. So the two basic setups for stoichiometry would involve Kc and Kp. Actually three, and Kq, you know. The KQ is a bit more complicated because in KQ, what do we potentially have? You know, like Kc are only dealing with all concentrations, and Kp are dealing with all pressures, but KQ you're going to have a mix of both concentrations and pressures potentially. You know, sometimes all concentrations, sometimes all pressures. But normally what we'll do is we'll just say A initial, right? This is A initial. This is B initial. You know, sometimes it could be zero. You know, for example, in the last problem we did, B initial was 0. G initial might be 0. Normally we don't have any products, but sometimes we start it backwards. You know, so if we have reversible reactions, we could go either way, forward or reverse. And so, you know, some of these may or may not be 0, or we might have quantities evolved, like in the example. Now, excuse me, allergy. There's going to be a change. Now, the change, the direction is normally what we would think is we go left to right, right? And so normally we think minus A, and we don't know how much the change is going to be. We just know it has to occur in these stoichiometric ratios. And so we call it minus AX, minus BX, plus GX, plus HX. It's a change. This is if the change goes left to right. But what if the change goes right to left, like in the last problem we did? Then, you know, the signs are just opposite. Plus AX, you know, we're forming reactants in this case, plus BX, and we're losing product. Minus GX, minus HX. Now, we know what the change is going to be because the change usually goes to the side with the zeros. I mean, can we have negative? Can you have negative 1 gram of anything? That just doesn't make sense. I mean, you could, if you had 20 grams and you lost a gram, no problem. But we got to start off with something. So if you have $0, can you give somebody $10? No, it just doesn't. Yeah. So it's the same thing. We go, you know, the change is into the direction of the 0. Okay. And so, how do you determine the direction of the change? There's two ways to determine direction. The first way is we look for the side with the zeros. You know, go to side with zeros. You know, so if I have 0 molar, the only way I can go is up. You know, I can't go down. That is, I can't lose any. I have nothing to lose. Or 2, if you can't tell, we do something called a Q calculation. Q is Q is something called the reaction quotient. Reaction quotient. And what the Q is this. You just take the ratio of the initials. So it would be a G initial to the little g, H initial, the little h dot dot dot. And we do the same thing as K, except rather than the initial values, let's see. What? Rather, K would have, rather than the initial values, what would K have? The equilibrium values. And so all you're doing is you're comparing this, the initial, to what it's supposed to be. You know, and so are the initial conditions close to K, or are they far from K? And if they're far from K, in which direction? And so we have a simple thing. If it's greater than K, you know, if Q is greater than K, that means we have too much product. Too much product. If we have too much product or too little reactant, it's the same thing. Too much product, too little reactant. Which direction should it go? Reverse. And so it would be, you know, plus AX plus BX minus GX minus HX. If Q is less than K, we have too little product. Right? Too little product, or in other words, too much reactant. And so it's got to go forward. What if Q is equal to K?
No change.
No change. Right? No change. The reason there's no change is because it's already at equilibrium. At equilibrium. So there should be nothing happening there. And then what we do is we figure out the equilibrium. At equilibrium, it's going to be A initial, plus, actually, let's say minus or plus AX. This is equal to A at equilibrium. And then over here, we got the B initial minus or plus BX, which is equal to B at equilibrium. We do the same thing with the others. G initial plus or minus GX is equal to G at equilibrium. And then H initial plus or minus HX is equal to H at equilibrium. And so we have this table like this. And what you're going to see is if you look at all the homework problems, you're just going to see a lot of variations. Sometimes what's missing? Sometimes X is missing. Sometimes, this initial is missing. Sometimes that's missing. And so what you do is you plug in as much as you can into the table and then try to solve for what's missing. That's our whole approach to doing these problems. But sometimes, as we'll see, sometimes there are going to be too many unknowns. Like, for example, the initial and X is missing. So what do you do there? And so if you have two unknowns and one equation, is that enough to solve it to a unique answer? If you have two unknowns, you need two equations. So is there another equation that we can write to help us solve these algebra problems? There's some other, we have the table here with a bunch of little equations there. Is there anything else that we could do? And there is. The other thing we're going to use as a tool to solve these problems is the K equation. The K equation is going to be G at equilibrium raised to little g, H at equilibrium raised to little h, divided by A to the A and B to the B. These are all equilibrium. Well, if we know the equilibrium, the equilibrium also equal, like for example, G equilibrium is also equal to G initial minus or plus G plus GX. And so we have lots of, things here. So the equilibrium value of G is just equal to G, we say initial, plus or minus GX. And this whole thing is going to be raised to little g power. Then H, initial plus or minus HX raised to the h power divided by, say, A initial minus or plus AX raised to little a power, B initial minus or plus BX. And so this is essentially what we're going to do. We're going to use these equations here to solve for the missing variables. And this is just algebra. So, and so we just set it up like this and see what's missing and then just figure out a way to solve for what's missing. What confuses a lot of people is, is that the stuff that's given in the problem initial, or is that equilibrium? So a lot of people get mixed up. I don't know, is that initial or equilibrium? And or there are other mistakes that people make. Sometimes they make a mistake in picking the wrong direction. But, you know, if you pick the wrong direction, then you get a weird value of x, you know. For example, if you pick the wrong direction, it's not fatal. You know? Let's say I misassign the signs here. Well, rather than getting an x which is a positive value, you get an x which is a negative value. So it still works, you know. It's not fatal. So if you're pressed for time, then don't even bother trying to figure out what direction. Just pick one and then solve it. Because there's always the double check. You know how we double check our answers? You know, after we complete this table, you know, we double check the answer. There's different ways. Sometimes the k value is given. If a numerical k value is given, then we can easily double check, did we get the right equilibrium concentrations by plugging in and saying if it equals the given k, the accepted value of k. K's are very important. If you look at the acid chart there, do you see on the right-hand column, the very far right, at the top of it, it says Ka. Ka just stands for acid. The Ka values are very important because those are all equilibrium reactions there. And so, you know, if you see something like a very large K, what does that tell you? It's pretty much all product, right? And so look at the strong acids there. They all have very large Ks, which means it's all product, which means, you know, are you going to find any HBr molecules in solution? No, it's all going to be H plus and Br minus, right? So, but for the weak acids, you'll see a numerical value there. If you look at the numerical value, you know, that's our check. You know, those numerical values are typically the average of multiple experiments, right? And so those are the accepted values. And then if you do a calculation, you better make sure that, you know, your numbers, when you plug them in here, compute to the accepted values within, you know, round off error, like that, hopefully. So the basic setup, and so let's look at applications. We already did 2 applications of this basic setup here. And actually, this is the basic setup for chapters 15, 16, 17, and 18. 4 chapters of just doing this kind of calculation. Seems easy, or does it? Does it seem easy? I mean, just setting up a table like this, it's not that difficult to memorize this table, is it? Yeah. Turns out it's not so easy. Because, you know, initially it's not so bad, you know, it's one equation, right? But later on we're going to throw in multiple equations, you know? And so there are multiple equilibria happening at the same time. So what do you do in situations like that? How does one equilibrium perturb the other? And so rather than having, let's say, one reaction, you have 3 reactions going on at the same time. What's happening there? So it can get quite complicated quite quickly. You know? But if you just have a single reaction, then it's not that bad. And so we're going to look at, in chapter 15, we're just dealing with pretty much just single reactions. Chapter 16, we start with multiple, with 2 reactions or more. Or multiple equilibria, I should say. Chapter 15 still isn't so easy sometimes because the math isn't so friendly. You know, so far the math is not so bad. And so let's take a look at this. Some problems here. Some problems that work on. The numbers here. All right, let's take a look at the number 33. Number 33 says this. Mixture consisting of 0.150 moles of hydrogen and 0.150 moles of iodine is brought to equilibrium at 445 degrees C in a 3.25 liter flask. What are the equilibrium amounts of hydrogen, iodine, and HI? And so mixture consisting, are these initial amounts here? A mixture consisting of, yeah, those are initial amounts. And so they want the equilibrium amounts. Now, there's something we have to keep aware of. What is the definition of amount versus molarity or concentration? So 1 molar, is that an amount? Well, in a way it is, 1 mole per liter, but do you know how many liters you have? Not necessarily. I mean, you could have a drop or gallons of stuff, right? And so 1 molar doesn't necessarily tell you how much. Whereas amount would be like a volume or moles. When I set up a table like this, are these what? Concentrations. These aren't amounts, these are concentrations. And so we don't plug in the moles here. Normally in stoichiometry you would do it by moles because the balanced chemical equation is a mole ratio. The mole ratio of the reactant. I forgot to do one thing, and that's Kp. What's the difference between a Kc and a Kp? You just replace all these, you replace with partial pressures instead. So it's the exact same table, but you just replace it with pressures. And the same thing here. We have Qc, this is Qc, and we also have Qp. Qp is exactly the same thing except initial partial pressures of all these gases. And so, pressure or concentration makes no difference. Whatever's easier. The table looks exactly the same. Just be consistent. When you do the pressures, do you do the pressures in torr or millimeters of mercury, or so you do it in atmospheres? All right, so let's see. We have the moles and we have the liters, so we can get the molarity of hydrogen. And so let's go ahead and do that. The molarity of hydrogen is 0.15 divided by 3.25. So I need to bring my calculator in. I have the calculator. I left it in my office, but I might have to go back and get it. 3.25. Okay, now we're allowed 3 sig figs, and like I said, I always carry. Let me erase this. I always carry 1 extra sig fig until the end. And so the reaction is hydrogen plus iodine. We got H2 gas plus I2 gas yields 2HI. What kind of reaction is this? This is an element plus element redox reaction. All these are gases. Actually, if all these are gases, we have a choice. We can go Kc or Kp. Which one should we do? We do concentrations, or do I calculate the pressures? We want to do the concentrations. Why? Because they gave us Kc, numerical value of Kc. And so the initial concentration of H2 is 0.0461, and I carry 1 extra. The 1 extra I carry a subscript to indicate that it's an extra digit. It needs to be rounded off later. And then, iodine's the same, so it's going to be 0.04615 molar. I just took the moles divided by the liters with the molarity. How much HI initially? 0. And now they want us to determine the equilibrium amounts of And so what else can we fill out in our ice table? The change. Which direction is the change going to go? Forward. And so this is going to be minus, A is 1, so it's minus x minus 1x plus 2x. The units here are molar, so we'll just keep it as molar. Do we know what x is? Is it 100% reaction? No, I mean, if this was Chem 1A, we'd say 0, 0, and double that. We're done, right? It'd be such a simple stoichiometry problem. But this is complicated because it's partial, And so let me write another arrow here. This is a dynamic equilibrium. And so once this dynamic equilibrium has taken place, has established, what are the equilibrium concentrations? These are the equilibrium concentrations here. Okay, now I have to solve for x. But how can I solve for x? No idea what x is. Yeah, right. We're given the Kc value. This is why we want the Kc value, because the K values are going to tell us, the final ratio that this has to be. And the Kc value is given here is 50.2. Now Kc changes with temperature, so we usually associate a temperature with these, 445 degrees C. What's Kc equal to? Well, Kc is going to equal the equilibrium concentration of HI squared divided by the hydrogen concentration at equilibrium and the iodine concentration at equilibrium. Well, we have those values here. These are the equilibrium concentrations. So we plug this in. This is going to be 2x quantity squared times 0.04615 minus x times 0.04615 minus x. This is a quadratic equation, so we'll figure out how to solve this. Let's solve this. Yeah, all right. Let's go ahead and try to work this out. This is going to be 4x squared on the top, right? And then we have to remember multiplying out binomials. Multiply these binomials, which is going to be, I don't like to do this, but it's going to be x squared minus a minus gives us minus point double that. 922. 0922. 0
Actually,
at
923, I guess.
923.
Forgot the subscript.
0.0923?
Yes.
Okay, and then we'll carry an extra digit, which should be 0. Is it? Yeah.
Yes.
And then
Square that.
square that. I'm sorry. Just give it to me in decimal form. Point
0, 0,
2413.
no, 213.
213. I don't, when you're dealing with these quadratics, I don't like to write exponential scientific notation. 213, is that right? And then give me one extra digit. 8?
Yeah.
Okay.
It would be 2129.
2129.
Yes.
Okay, never ever round intermediates, right? You never round. Because what that does is it adds a little bit of error, and each time you round, you add a little bit of error potentially. And those errors are cumulative. They just add up. And by the time you get to the final answer, you could be significantly off. So what we try to do is not do any rounding until the very end. even this extra digit we carry, we never round. You know, we just use it as it is. So let's say it's a 9-9. I wouldn't bother rounding this up. I just drop the 9.
Shouldn't it be plus the last one?
Yeah.
Plus. Okay. Yeah. This is equal to 52. And so then we got to go 50.2 x squared minus, what's 50.2 times this? 4.633 x plus, and 50.2 times that?
0.1069. No, 0.1069.
0.1069. 0?
0.1069.
Oh, okay, got it. 0.1069 is equal to 4x squared. And then let's subtract the 4x squared from both sides. So we get 46.2x squared minus 4.633x plus 0.1069 is equal to 0. Okay, now you have two choices here. You could use the quadratic formula if you like, or you could use your calculator that solves quadratic equations. For those of you who like the quadratic formula, x is equal to negative b plus or minus the square root of b squared divided by 2a. Okay, and then you're going to get two x values. You pick the one that makes sense. Usually the positive one makes sense. You know, we can't go negative, polarity. And so one of these won't make sense, the other will make sense. Does somebody have the calculator?
0.0359.
Okay, x is equal to 0.0359.
Yeah.
Okay. 0?
99.
99. All right, we're going to carry this 9. Yeah. All right, now let's go ahead and figure these out. The equilibrium hydrogen should be 0.04615 minus 0.03599. And that gives me what? 0.0102. Well, let's go. I'm not going to round it. So 15 minus 9 is 6. And then 10 is 1. 0, 1. 1016? Okay. Molar. Now, this is what we call the equilibrium concentration of hydrogen. Iodine should be the same. So 0.01016 molar. And the iodine should be double this. So can somebody double X? Let's see what we come up with.
107.
Plus 1827. 2, 719,
98.
98, 7198 more. I'm going to carry these extra digits because sometimes they help when we double check our answer. As we did all this math, it's easy to make a mistake, right? And so what we want to do is we want to double check. The way we double check it is just to calculate the K based on our values here. So it's going to be 0.7198 squared. And again, we ignore the units, and it's going to be 0.01016 for the square. And so you could just take 0.07198 divided by 0.01016 and square the whole thing. Hopefully it comes out to 50.2. Hopefully. Did it?
Yeah.
What does it come out to? Actually, give me more digits.
50.192.
50.192. Is that close enough for a round off error? Yeah. In fact, it rounds to 50.2, and this is what you're looking for. If you start doing a whole bunch of rounding steps in the middle, when you do your double check, sometimes it can be way off. And you don't know, is it way off because you were doing round offs, or is it way off because you made a calculation error? And so it helps to carry extra digits to make sure you're not making a calculation error, and that you don't have, you carry extra digits to minimize a round off error.
Is it that equation have another value of x?
Yes.
So if two of them, so how can we know which one that we?
Because the other value will be negative.
It's positive then.
It was like 0.06.
Yeah.
Okay, 0.06, 0.06. 0.06, 0.04 minus 0.06 gives you
Negative.
negative. Can you have a negative molarity?
Mhm.
No, it doesn't make any sense.
So, but like, we have to write it down, or just choose the one.
Just choose the one. One of them will work, the other is definitely not going to work. It'll either be a negative value, or it's going to result in one of these concentrations or more being negative, and it's impossible. Impossible.
But it's like, it will like, it's still smaller than, for example, it's like 0.0.
That's not going to happen. It's
No.
not going to happen.
Okay.
Yeah. Don't worry about that. If it does happen, then something's wrong. Unless, the only time it might happen is for higher order. For higher order, you could be, but it depends on how complicated it gets. But typically, even for the higher order, we're okay. All right, so we're done. We have the equilibrium concentrations here. You could either leave these as is, or you can round them right now. What? Oh, yes, you're right. We aren't answering the question because they're asking not for concentration, they're asking for amount. And so we need to go from molar to moles. And so we need a volume for that. And so what we do, the last step would be times 3.25 to get the moles. And so times 3.25, actually go ahead and someone do that. Liters will give us
0.033.
0.03302 moles. And so we end up with that many moles of hydrogen, and the same for iodine, and then for HI,
0.2339.
0.2339 moles. Now, why don't I just use moles instead of molarity? One reason I don't is because Kc it uses concentration. If K was based on moles, then I'd use moles, but K is based on concentration, so I must use concentration. Sometimes moles and concentrations will give me the same answer. Sometimes not. And in this case it would. You know why it would? It's because the units cancel here. If I look at this is going to be moles, molarity is moles per liter. And so I have moles per liter squared, moles per liter times moles per liter. And so the volume cancels out because I got volume squared up on top, volume squared on the bottom, the volume cancels out, and so mole ratio is the same thing as the molarity ratio. But if I did this, it wouldn't cancel out because I'd have liters squared on the bottom here and liters on the top, and the liters don't cancel out, and so the mole ratio does not equal the molarity ratio. And so sometimes you can get away with using moles. Saves you a little bit of time. But most of the time you can't. And since most of the time you can't, then most of the time I'm just going to use molarity. Some people absolutely don't care. Every semester I have a few people who, always use moles and always get the wrong answer, but won't change. The guy used the molarity, not the moles, right? They get lucky once in a while. They get the right answer, but it's wrong. Okay, let's show us the next problem. Let's do it. need to write these. I should write this down. All right. Okay, we're going to look at number 35 next. So this is 33. It's 35. Starting with a 0.3500 mole, starting with 0.3500 moles of carbon monoxide gas and 0.0500 moles of COCl2. You know, COCl2, what is that? Is that monocarbon, monooxygen dichloride? Did you learn the naming system for that? Or carbonyl chloride. No, you didn't. You don't have to worry about that. In a 3.050 liter flask at 668 Kelvin, how many moles of chlorine will be present at equilibrium? So again, they're asking for amount, but we need molarity. We need concentration to clear out the table. And so let's go ahead and set this one up. So to give us the reaction, for number 35 is carbon monoxide gas plus. What kind of reaction is this? Cl2 gas gives us COCl2. What kind of reaction does this look like? Looks like a redox reaction. That's correct. What's the oxidation? Well, we can do a quick check of the oxidation states here. Oxidation state on carbon or oxygen? Oxygen goes first at 2 plus 2, 0. Now, which one goes first here?
Oxygen.
Oxygen or chlorine? Chlorine at -1. This is tricky, and so if you ever have a case where I don't know which one should go first, it's usually the most electronegative one that goes first because the most electronegative one wants its oxidation state. And so usually we would do something like oxygen at -2 and chlorine at -1, and then carbon would be +4. Or we could just draw out the Lewis structure. If we draw out the Lewis structure, we would have gotten the same. All right, so to give us the initial amount of carbon monoxide, we'll just convert that into molarity. So can somebody do this? 0.3500 divided by 3.05? 0.1147?
Yeah.
Okay, this case we're allowed 4 sig figs, so I'm going to carry a 5th digit. 475?
Yeah.
Chlorine?
01803.
01803
Sub 2.
sub 2. COCl2?
Oh, sorry, that was
Oh, that was for COCl2. So. 018. Can you repeat? 03 sub 2. More. Cl2? 0. And so we know which direction must this reaction go. Yeah, it's got to go to the left. So this is going to be plus 1x molar, right? Plus 1x molar. So I don't have to put the 1 there. Minus x molar. And so that would be the proper direction for this. So at equilibrium, we have 0.11475 plus x molar, x molar, 0.018032 minus x molar. And what is the K value for this? The Kc value is equal to 1.2 times 10 to the third at 68 Kelvin. Well, the last K value was what? The last K value we did was 50.2, which tells you, does it really favor one side or the other? No. You know, it's kind of a seesaw type thing. This K is kind of a bit bigger, and so this K kind of favors the product side. You see, because it is 1,200, 1,200. It favors the product side. If it favors the product side, do we expect to lose much product? No. And so we say that the change should be small, right? The change should be small. So we need to solve for x. We can just plug this into the Kc expression here. Kc is going to be the COCl2 concentration at equilibrium divided by the CO concentration at equilibrium and the Cl2 concentration at equilibrium. And then we'll just plug in these here. You know, the COCl2 concentration at equilibrium is this 0.018032 minus x. Again, no units. And then 0.11475 plus x. And x. This is another quadratic. And it gets tiring. Even multiplying, even if you have the fancy calculator, you still have to get this into quadratic form. And so we have something. If you think the change will be small, try the SA. SA stands for simplifying assumption. So let's try the SA. The SA would be something like this. For the product, we would say 0.018032 minus x. We say that x is so small, it's like, yeah, it's negligible. It's not zero. It's just, it's not going to make an impact on this. The way we can visualize that is, let's say somebody were to go and remove a drop of water from the swimming pool. If somebody removes a drop of water from the swimming pool, are you going to worry about, now I got to recalculate the volume of the swimming pool, right? No, you wouldn't worry about it. And so sometimes the change is so small it makes no impact. So the change happens, you know, in the insignificant digits here, so it's negligible. But okay, that's that. And so what we'll say is that it's approximately equal to 0.018032. That is, it just doesn't change that much. There's not much of an impact, right? And so here, 0 plus x is the next one, right? 0 plus x is the next one. So 0 plus x should be 0. So if somebody were to remove a drop of water from the swimming pool, you know, that's something. But if somebody were to remove a drop of water from the, let's say, you know, you could ignore it. It's no big deal, right? One drop of water. But let's say you were out in the desert and it was you haven't had water in many days, and is a drop of water significant? Yeah, a drop of water would be significant. So if you have nothing, then you can't ignore this, right? Because nothing is. And so 0 plus x is equal to x. Right? Because this is nothing, and so any change, no matter how small it is significant compared to nothing. Here, we got something here, so this might be small compared to that. And we can try the other one. 0.11475 plus x could be simplified to 0.11475. This is called the simplifying assumption. And what the simplifying assumption does is it just makes the math a lot easier. And so here we go from a quadratic like that to this. We get the 1.2, I'm going to leave some space here. 1.2 times 10 to the third, which is our k, is going to equal 0.018032. We've lost the x. Divide by 0.11475. 0.1475 times x. We don't lose this last x down here. Why didn't we lose this x?
If that was 0, then it wouldn't be a
Yeah.
answer.
Because that's this one, right, where we have nothing and we add something to nothing. Something to nothing is always significant. You can't ignore it. Now solve for x. Do you see how much easier that is? So we don't, well, that's the question. We're just guessing we can do that right now. I don't know. If you think,
So what would make us think?
what would make you think is this? It's more biased towards the product, right?
What is the difference in time?
That's a problem. And so, you know what we're going to do? We're going to do this crazy justification for this. The crazy justification is taking a wrong answer and justifying it because the wrong answer is not so wrong, kind of thing, or the wrong answer didn't change so much. All right, and so this is the way we're going to do this. But I'll explain it because I'm going to show you the justification because we can't just go ahead and do it, right? Assume it's going to work. And so sometimes it works beautifully. That is, you make the simplifying assumption, and it doesn't matter if you spend an extra 10 minutes doing the quadratic, you would have gotten the exact same answer. That's where it works nicely. But let's see if it works nicely here. We just tried it. You know why we try it and see if it works or fails? Because it's so quick. You know? If it works, great. If it fails, well, you didn't waste too much time. Right? And so we try and see. Well, what does x come out to?
0.000130975.
Okay, we're allowed 4. Are we allowed 4? Ah, no, we aren't even allowed 4. How many sig figs are we allowed? All right. No. 2. Yeah, because of k. So 0.000130. That's my x. Okay. Now here comes the circular justification. You know. The circular justification is this. If the biggest percent change with calculated x is less than 5%, then okay. And so where would the bigger percent, you know, taking x from 1147 or taking x from 180? What would be a bigger percent change?
From 0 to 80.
X taking from 1147 or x taking from 180?
From 0 to 80.
From 180, right? It's like, what would be a bigger percent change? Taking a drop from a swimming pool or taking a drop from a water bottle? What would taking a drop from a water bottle would be a bigger percent change. You know, even though the drop is the same, right? What you're starting with is, Yeah, and so what we look for is the smaller the initial. And the change is x here. And so what we do is we calculate the percent change like this. The percent change is going to be the change divided by the initial times 100%. And so we look for the biggest change. Well, the biggest change, x, is the same. So the biggest change is going to be 0.000130. Sometimes the change is 2x. Sometimes the change is 3x, depending on the stoichiometry. So sometimes we have to multiply it. Divided by the smallest initial. The smallest initial is going to be 0.018032 times 100%. And this gives us what? 0.72%. 0.72% means we're less than 5%. So it's justified. If the percent change is too big, then our assumption that it's a small change is wrong, right? And we can't ignore it. So it's a little bit circular, but anyway. So what do we do with our calculations? So should I say the equilibrium is equal to 0.11475 molar? No, because that would be double error. I'm introducing an error by making the assumption, and then I'm introducing an error by totally ignoring it. And so even though even though I ignored it here, I'm not going to ignore it here. And so I'm going to add it. Yeah. I'm going to add the value that we just did. And so what I'll do is I'm going to go over here and do 0.11475 plus x, which was 0.00013. 0. And so this gives me 0.884110. And so, was the change all that big? It wasn't that big of a change, right? But still, less than a 1% change. Much less than 1%. But still, it's, you want to factor that in. Over here, this is going to be 0.00130 molar. And then over here, we're going to go ahead and calculate 0.018032 minus 0.000130. And so that gives us 209,710 molar. And so we lost a little bit. Yeah, we're going to change it to moles, but before I change it to moles, what should I do?
Sure.
I should do the double check, right? Because in this case, the mole ratio will not equal the molarity ratio. And so let's do our double check here.
And it should be like close enough, right?
It better be close enough. This is where we see, is a simplifying assumption valid? If our double check came way off, then maybe it wasn't such a great idea. Maybe we should tighten up the restriction on the simplifying assumption. And so we're going to do our double check and see by calculating the value of K based on our calculated equilibrium concentration, 0.017902 divided by 0.11488. 0.000130. Hopefully that comes out somewhat close to 1.2 times 10 to the third. What does it come out to? $11.98. And then if you round this to 2 sig figs, we got 1.2 times 10 to the third. And so this looks good, right? Looks good. Now, if you use the quadratic equation, would you have gotten a better answer? Yes, you would have. But it depends, because the percent change was 0.7%. If the percent change was 4%, for sure you'd get a better answer using quadratic, but it's acceptable. There's some error there. But oftentimes the percent change, when you calculate it, comes out to like 10 to the minus 6% change. If you got a 10 to the minus 6% change, there's no use in doing the quadratic because you get the exact same answer. It's such a small change. The simplifying assumption is very valid. All right, so the simplifying assumption is quick and easy, and it can save you a lot of time. And so that's why we do it. But does it always work? No. We try it and see. For example, let's take a look at number 36 next. Number 36 is 1 gram of each carbon monoxide, water, and hydrogen are sealed in a 1.41 liter vessel and brought to equilibrium at 600 Kelvin. We didn't finish this problem, right? No, because they're asking for the moles, so I didn't complete it, but I don't want to complete it. Yeah. You can complete it. 36 is going to be carbon monoxide gas plus H2O gas, steam. We yield carbon dioxide gas plus hydrogen gas. They give us a Kc for this one. And so we got 1 gram of carbon monoxide. And so let me calculate the molarities here. So and carbon monoxide, carbon's 1201, oxygen is 16, so that's going to be 2801. So divided by 2801, and then that gives us the moles divided by 1.41 liters. And that gives us the molarity. Now the molarity, is kind of small. This is going to be 0.0001168 molar. All right, and then water, if I have 1 gram of water, 1 divided by the molar mass of water, 1802, divided by the volume, 1.41, gives me 0.0393, so 5 molar water. And then hydrogen, we got 1 divided by 1.016, we'll do that. No, 2.016. So 1 divided by 2.016 divided by 1.41, 1.351. Molar. So those are initials. Okay, now what we're going to do is figure out the direction. What about the carbon dioxide? 0. And so the direction has got to be forward. Minus x, plus x, plus x. And then at equilibrium, we have 0.0001168 minus x. 0.03935 minus x. X molar 0.3517 plus x. Now,
Is it going forward or?
Yeah.
Why is it going?
It can't go backwards because of the 0. We always go in the direction of 0. Kc is equal to 23.2. 23.2 tells you it's going to be kind of seesaw, balanced. Maybe not perfect, but close. So you expect both products and reactants. And this is just going to be the CO2 concentration times the H2 concentration. These are all equilibrium times the carbon monoxide concentration times the water gaseous water concentration. Q. Pretty soon I'll stop writing these Q. No. And so this is going to be x times 0.3517 plus x divided by 0.000168 minus x.
How do you get the carbon monoxide, the molar mass? No, I mean the molarity is 0.001168.
Is it wrong?
Yeah.
Okay, what is it?
0.025.
0.025? 0.025? 3? 1? So I can count on you guys to catch any errors. That's good. So 0.02531. Otherwise, I'd have to double check everything. And 0.03935 minus x. All right. We can just go ahead and do the
Simplifying assumption.
well, why not? Do the simplifying assumption. SA, right?
K is too small.
Well, let's just try it. So this is going to equal x times 0.3517 divided by 0.202531, 0.03935. So can somebody calculate x?
Zero point zero six five six nine.
0.06569. All right, now we pick the smallest value. The smallest initial would be this one here. And so just looking at this, it's way too big. It fails, right? It's failed. It's more than 100%. And so we can't use it. And so it would tell you when it would fail. And it should fail, and it did fail, so that's good, right? Now, the other thing we could do is we could do a partial simplifying assumption, you know. The partial simplifying assumption would be, maybe these two are smaller, right? But this one is like 10 times bigger. And so maybe we just do the simplifying assumption in the numerator here and leave these ones alone. We could do that too. But still it comes out too big. And so we don't have to do a simplifying assumption on each. We just pick the one that's most likely to work. And then hopefully that saves us some math. And so what do you have to do? Quadratic. But I'm not going to finish this one. This quadratic takes a long time. Okay, let's see which ones I want to do next. I should write this down. Okay. Are you guys okay with the simplifying assumption? Yeah. I'm going to show you another technique that might help simplify your life, and that's for number 41. Or is it number 41? No, number 40. But before I talk about number 40, I need to talk about, have you ever heard of Le Chatelier's principle? We'll talk about Le Chatelier's principle. let's say we have a system that's already at equilibrium. You know, everything's balanced. There's no net change. Le Chatelier's is perturbing or upsetting a system at equilibrium. And so if something's already at equilibrium, you know, let's see, like here, you know, this system's at equilibrium. You know, these are the equilibrium amounts here that we need. But if somebody goes and injects some more SO3 into this equilibrium, then that's called a perturbation. And so if you put in more SO3 in here, well, now you got too much SO3. The system will compensate to reestablish a new set of equilibrium conditions. And so here, if I inject more product, I'm going to have too much product, so I'm going to get net reverse reaction to compensate. And I'm going to get a new equilibrium established. The new equilibrium is going to kind of look similar to the original, but it's going to be different. All right. And so we have two ways we deal with Le Chatelier's. We do it qualitatively and we do it quantitatively. And so, for example, if I inject more nitrogen, what's going to happen? Well, it's going to set it, it's going to shift it to the right. More hydrogen shifts it to the right. If I remove hydrogen, it shifts it to the left. You know, that kind of thing. Now, when I add more, I'm talking about impacting concentration or pressure. You know? And so changing the concentration or pressure of those will do it. But there are other things that can happen too that are kind of weird. I don't add or remove anything, but I squeeze down the volume. Let's say this system was at equilibrium, and then I decide I'm going to squeeze it to half the volume. If I squeeze it to half the volume, is it going to stay at equilibrium? It turns out no. If I squeeze it down, then equilibrium is going to favor the side with less gas. You know, if you squeeze it down, on the left we have 4 moles of gas, on the right we have 2 moles of gas. So squeezing it down is going to push it to the right because you have fewer moles of gas. Okay? If I expand it, then it's going to favor the side with more moles of gas. There are other ways to change things too. You know, we can change the pressure, but we can change the pressure. If I add, let's say, if I add argon gas to this and increase the total pressure, and so rather than, let's say this was originally at 1 atmosphere, but I'm going to add 99 atmospheres of argon gas and get 100 atmospheres of total pressure. If I have 100 atmospheres of total pressure, is that going to change this? No. It's not going to change this because does argon participate in this? No. The partial pressures of these gases didn't change. It would have to be, if I increase the nitrogen, if I increase the hydrogen pressure, for sure that's going to change it. But if I just throw in some inert gas, it has no impact on it. Does that make sense? No? Yeah.
What's the difference between the impact of other gas and you increase the value or decrease the value?
Okay. If I, let's say I have A and B here, right? These are gases. If I cut down the volume, you know, let's say I cut down the volume by a quarter, what just happened to the pressure? It increased. So the pressure of A increased 4 times and the pressure of B increased 4 times. Well, you think, well, the pressure of both increased by the same amount, right? And so that shouldn't have an impact on it, should it? But it potentially could have an impact because if one is the product and the other is the reactant, it depends on the Q. It depends on what power we raise it to. So for example, if B is raised to the 3rd power and A is raised to the 1st power, then all of a sudden we have 4 times the pressure raised to the 3rd power versus 4 times the pressure raised to the 1st power, which totally changes the ratio. You see the ratio is going to change. And so the impact there is because of these coefficients. But let's say there's another way to increase pressure. Now, if I leave this the same size, A gas and B gas, But now I introduce C gas, but C gas doesn't participate at all. You know, and so I add a whole bunch of C gas in here, and now the pressure is skyrocketed. But A gas and B gas, did the pressure change for A gas and B gas? No, because I have the exact same amount, so I'm going to have the exact same number of collisions with the wall. You know, the partial pressure of A will be the same, the partial pressure of B will be the same. It's just C gas is now extremely high. Something like that. And so this is Le Chatelier's principle. And so qualitatively, we predict little shifts here. And we can also do this with thermodynamics too, but thermodynamics is interesting. And so you could read about it here. Add or remove gaseous reactant product, it's going to shift it. Add an inert gas, no change. No gas. Change the pressure by changing the volume, it changes. Now, if both sides have the same moles of gas, like 2 moles of gas going to 2 moles of gas, then expand and contract doesn't do anything because neither side favor. That's Le Chatelier's principle. And so let's take a look at this. Yeah. So we're going to look at this one, this dinitrogen tetroxide and nitrogen dioxide problem here, number 40. Which is, equilibrium mixture. So it's already at equilibrium, and the flask on the left in the figure is allowed to expand into the evacuated flask on the right. And so here I have this. This is at equilibrium. And so if I calculate the ratio is Kc here. It's at equilibrium. Should be no net change. Okay, but if I open this valve, what's going to happen? Will it shift to the right? Will it shift to the left? Or will there be no shift? Well, if I open this valve, what happens to the volume? The volume increase, so it should shift to the right. We could, the way we could figure that it's going to shift to the right is we could do a Q calculation. If we do a Q calculation right now, Q is equal to K. But if we redo the Q calculation with the new molarities, because we have the moles here, now the volume's increased from 3/4 liter to 3 liters. Recalculate the molarities and then plug those into Q, we see it's too small. It's got to shift to the right. And so we could do a Q calculation to figure it out, but we don't need to because we can see what's going to happen. It's going to shift to the right.
So the professor, Kc will always remain the same no matter what conditions
Kc remains the same as long as the temperature is fixed. K doesn't change, so. So, this was a system at equilibrium. We perturb it, and now it's no longer going to be at equilibrium. So, I'm going to show you the different ways to calculate this. There are different ways we think about when we perturb systems. And so, originally it was an equilibrium. So, this is number 40. And this is kind of a long way of doing it. I do it the long way, and then we'll do it some short ways. And so we got N2O4 gas. This is going to 2NO2 gas. And so the system's at equilibrium. Initial equilibrium. Initial equilibrium is going to be 0.971 moles divided by 0.75 liters. No, not 0.75. Yeah, that's right. What does that come out to? So, someone have it? I want the molarity. I'm dealing with Kc. And we should do Kp calculation too eventually. But they're, exact same thing. 1.294 molar. And then I got 0.0580 divided by 0.75. So let's go ahead. Sometimes I'll write that here. It doesn't matter. You can write it if you want, but just calculate it. 0.058 divided by 0.75. We have 0.0773 molar. Can we verify that this is at equilibrium? Go ahead and do that. Let's calculate our Q up here. Our Q is going to be NO square divided by N2O4. And so we got 0.07733 squared divided by 1.294. What does this give us? Point 0046 1 7. Close enough to this 4.61 times 10 to the minus 3. Right? Okay, now we're going to perturb it by increasing the volume. And so we perturb it. So this was the original moles per liter, but now we have 0.971 moles now divided by bigger volume. What's the new volume? 3.0. We got to have both, so it's going to be 3.00 liters. Right? And what's this one going to be? This is going to be 0.0580 moles of NO2 divided by 3.00 liters, which gives us our new perturbed initial. Perturbed. And so what are those concentrations here?
Point 3236.
0.3236 molar and
0.0193.
0.01933 molar. Okay, now let's calculate our Q value here. And calculate our Q value here is 0.01933 squared divided by 0.3236, which gives me a Q value of 0.001154. Okay, this is smaller than K. If it's smaller than K, this is equal to K or close enough to equal to K, right? I mean, those are the values it gave us. This is smaller than K, which means we shift forward. Just like we expected, by increasing the volume, we favor the side with more. And so the shift here, this is going to be the Le Chatelier shift, call it. The Le Chatelier is we take our initial equilibrium, perturb it, which upsets the conditions, makes them non-equilibrium, and now we got the shift. This is going to be minus x, and this is going to be plus 2x, because of the stoichiometry. For every x, we've got to gain 2 to the power 2x. And so at equilibrium, we got 0.3236 minus x molar, and 0.01933 plus 2x molar. Now all we have to do is figure out what x is, and then we can get the new equilibrium conditions, after this is reestablished. To figure out what the x is, we just plug it into the k equation up here, and so we get 0.01933 plus 2x squared divided by 0.3236 minus x. And then solve it. Okay? I would let you solve the quadratic here, but there's there is one additional trick I want to show you. to simplify the math. What we had was we had the simplifying assumption, right? The simplifying assumption. The next trick, solve as usual, or try resetting the initial conditions. Let me just go through a brief rundown of what resetting initial conditions means quickly. And then 10 minus 3 favors the product or favors the reactant? Favors the reaction. So the way I visualize this is like this. Let's say I have a water container. Actually, I'm out of time. I'll do this. I'm going to do this next time. I'll stop here.